Hello everyone and welcome to Chapter 15 of Phase 2, that is Programming with TensorFlow. Chapter 15 is Simple Linear Regression with Optimizer. Now, optimizers are the extended class which include added information to train a specific model. The optimizer class is initialized with given parameters, but it is more important to remember that no tensor is needed here. The optimizers are used for improving speed, performance, for training a specific model. Now, these are many of the optimizers available in TensorFlow, which we will make use of when we move on to neural networks and especially convolution neural networks. I just name them one after the other. Stochastic Gradient Descent, also called as SGD. Then we have a Stochastic Gradient Descent with gradient clipping, momentum, Nesterov momentum, Adagrad, Adadelta, RMSProp, Adam. Now this is something that I usually prefer for my deep neural networks. We'll have a look at all of them when the time comes. And this is just an image for an image's sake, nothing much over here. This is the 15th chapter and these are the lines of code. We have kept the equation same as it was previously. This time we are not going to specify the values of W and B. Rather, it will be the job of the optimizer. After that, we have got learning resources which are pretty much common as compared to chapter number 14. So let's get started with. Okay, so here we are, chapter 15, Simple Linear Regression with Optimizer on Jupyter Notebook. The points of x and y are still the same as chapter number 14, but this time we don't know the values of w and b, and it will find it out on its own using the optimizer. As you can see, I had run these lines of code previously. If you want to start fresh, all you have to do is click on kernel, restart and clear output. We'll wait for some time, doesn't take too long, depends on the processing power of your computer. There you go. The first line of code, as usual, import TensorFlow as TF, and this time we are going to start with the value 0.8 and minus 0.8 and let the optimizer do the job instead of feeding in the actual values of -1 and 1, which satisfies the equation y is equal to mx plus c. We run this as well, this time as well. We have x and y as placeholders, float 32 type. Our linear model is still the same, w equals mx plus c, wherein c we are calling it as b, doesn't matter, you can change it the way you want to. As we had discussed previously, squared will find out the error, which could be positive or negative, but using tf.square it will convert all of those into positive values. What it does is it will find out what it got from this equation by applying different values, and then it will deduct y from it. Y is the original output or label that we want, and it will continuously keep on tracking till the point that this value squared becomes low or pretty much 0, right? After that, by passing the value of squared and using the method tf.reduce underscore sum, we will get the value of loss. 0 means it fits perfectly. If the value of loss is large numbers, then we don't have the right values, and slowly using regression it is trying to find out the best loss possible. Now there you go, selecting an optimizer. If you remember, I had talked about Stochastic Gradient Descent, in which Gradient Descent Optimizer is currently what we are using. It is a part of SGD. Now this is called the learning rate, which is 0.01 right now. We'll be making use of learning rate when we move on to deep neural networks. As of now, just consider it as the small steps it will take till the point the equation converges and gives us the right values. If we have a very small value of learning rate, it will take us a lot of time to converge to the answer that we need, and if we have a very high learning rate, we might miss out a few key steps and not get the perfect answer that we want. So it's always a trade-off. We need to play around with this value, and there is no hard and fast rule on how to decide this value. Here I'm starting with 0.01, and I would request you to start with the same value. Now we are calling this as an optimizer. You can rename it the way you want. Let me run these 2 lines of code, and after that, whatever is the output from optimizer, we are going to minimize the loss and put it to a variable called train. After that, since we are making use of variables, init equals tf.global_variables.initializer. We're going to start our session with the name SESS. We're going to run the session with the value of init. Now what we're doing here is we are going to run this loop for a duration of 10,000 times, wherein the optimizer will try out different values, the starting ones being 0.8 and minus 0.8. It will try with positive as well as negative values. It will do it for 10,000 times for the values that we have given, and it will give us the values of W and B, that is the best fit line. We run this, and based on the processing power of your laptop or a computer, it will take time. So now that we're done, let us check, and we already know that at W equals -1 and B equals 1, the equation, which is linear model equals Wx plus B, fits perfectly. So let us find out the values. Perfect. And like I told you, they don't usually give you the perfect value, that is not -1 and 1. The reason is the learning rate. If you wanted it to be a precise 1, then you have to play around with the learning rate so that this value is incremented. For such a thing to happen, we might have to use a learning rate like 0.0000000001. So you get my point. And eventually it will turn it to the number 1. But then again, we have a pretty close value, W equals -1 and B equals 1, wherein it fits perfectly. Let me close the session. And what I want you to try now is find out corresponding values of X and Y, which fits a line perfectly. Start with any random value of W and B. Run this line of code. You can choose the number of times you want to run this loop, and eventually you'll have the answer here. And that is the power of TensorFlow. And using optimizers, currently gradient descent optimizer here with a learning rate of 0.01, we converge towards our answer, that is W equals -1 and B equals 1. I hope you enjoyed today's session as well. I'll see you again the next time with more interesting content. Till then, have a good day. Bye.